Good morning, everyone. Today we present our Ee466 project on designing a protection mechanism for the IEEE 9 bus power system. In this presentation, we will walk you through system protection basics, followed by specific protection strategies for generators, load, transformer, buses, and transmission line, concluding with our final protected design. System protection is initial to identify and isolate faults within a power network. We use CTs, BTs, circuit breakers, and relays to improve system stability and minimize equipment damage. Component to protect: we focus on protecting generators, load, transformers, buses, and transmission lines, each requiring tailored protection strategy. IEEE 9 bus here. This is IEEE 9 bus used for simulation. It includes 3 generators, 3 loads, and interconnecting line and buses simulating real-world grid behavior. For designing protection for generators and load. Generators are protecting using overcurrent relays connected to CTs. This detect excessive currents and trip the breaker to prevent damage, as shown here. I wish it's clear. Okay. For the load protection, similar to generators, lamp load are protected using CTs and overcurrent relays to isolate them in case of overload or fault. Designing a protection for transformer and buses. Here in transformer we have two types of protection: internal protection and external protection. In the first one, we use differential relays to detect internal transformer faults by measuring current imbalance at both ends. Here, okay. The second one, external faults are also detected by differential relay, providing protection beyond just the transformer body. Thank you for listening, Professor Mohammed Traib. Now I will give the microphone to my friend Fatima.
Now, let's start with the protection we designed for the transformer and the bus. Well, for internal transformer fault, we use differential protection. How? We place CTs on both the primary and the secondary side of the transformer and connected them to a differential relay. So in the simulation, we introduced a fault that mimics insulation failure inside the windings, and the relay immediately detected the current imbalance and isolated the transformer. Furthermore, that improved the speed and accuracy of the protection method. For external transformer fault, we extended the CT placement to nearby terminals and adjusted the relay settings so when we simulated a fault outside the transformer, the relay detected it. But it didn't trip immediately. And instead, the system allowed the line relay to respond first and the transformer relay to act as a backup. And this shows the good coordination between the protections while avoiding unnecessary tripping. Now, for the bus protection, well, buses are a critical part of the system, so we applied also a differential protection. Here we placed CTs on all the incoming and outgoing line connected to the bus and used differential relay to monitor the total current balance. And when we simulated a fault directly on the bus, the relay picked it up immediately and isolated the faulty bus section by tripping the breakers. And this confirmed the relay's speed and selectivity and showed that the protection works exactly as intended. Now, let's talk about the transmission line. Well, these are the long-distance highways of electricity, and they are very exposed to fault like lightning strikes, line contact, or environmental condition. So they need a special kind of a protection that can locate the fault quickly, even if it's far away. And that's why we use distance protection, which relies on impedance measurement. As I said, transmission lines are long and exposed to many types of faults, like weather issues or insulation breakdowns. And to protect them, we use a distance relay. This relay calculates the impedance between its location and the fault point using signals from both BTs and CTs. So the protection was divided into three zones. Zone 1 trips immediately for a close fault. Zone 2 and Zone 3 responds with time delay for the fault farther down the line. In our simulation, we tested faults in all three zones. So in first zone fault, the relay tripped immediately. For second and third zones, the relay worked with the correct relay. And this proved that the relay settings were properly configured and that the system can clearly distinguish fault locations. So the transmission line is now fully protected from short distance to long distance faults with fast and reliable repair. In conclusion, our project was about designing a complete protection system for the IEEE 9 power network. We focused on protecting every critical part of the system: generators, loads, transformer, buses, and transmission lines. For each component, we applied industry standard methods using relays, CTs, BTs, and circuit breaker to detect faults early and isolate them quickly. And this coordination between protection elements help improve system reliability, reduce the risk of damage, and ensure smooth operation even under fault condition. And by combining smart design with fast acting protection, we built a safer and more resilient power system. And finally, this is the final design after protecting the system. Thank you so much for your time